Uh, Hello everyone. So can someone acknowledge if I'm audible or not? Even the screen is visible or not?
Good morning, sir. Yes, you're audible and your screen is visible, sir.
Okay, okay, great. Thank you. So right now there are about 160 students. So how many are supposed to join? Like more than this, or everyone has joined now? The participants are about 160.
Yes, sir. Some of them are in the classroom, sir. We are using the projector to display the
Okay,
class. So we can start, sir.
okay, nice, nice. Okay. So okay then now it is, yeah, I'll start right now, right away. So okay, thanks. Okay. So, hi, students. I think I already gave you lectures on ML or data science last semester, I guess. I don't know if it is the same section or not, but hopefully you know me. Yeah. So I'm Narendra. I'm actually currently staying in IIIT Hyderabad. Uh, Actually, your college Kite and IIIT has an MOU also. So many of the external faculty that you see, most of them might be coming from IIIT Hyderabad. So coming to me, actually I like NLP. So that's why I did my PhD also in NLP only. So all the topics that we have here, about 12, actually we have 12 experiments in this lab. So yeah, so these are all also once part of my curriculum as well. So I learned these things as a student, and I did research in NLP itself. So about 5 or 6 years I spent my life in researching NLP. So actually after this we are touching upon word to work and all. Maybe this is your second year. Maybe by the time of third year and fourth year, you will be introduced to much more complex, much more interesting topics as well. So we'll treat this as a basic class. Uh, yeah. Now we'll jump into the experiments. So second year, second semester. So we have 12 experiments. Today I'm planning to cover 10 experiments from 1 to 10. Yeah. Uh, it has first basics, like how to use regular expressions, and then perform pre-processing tasks such as lemmatization, stemming. That is second experiment. And the third experiment is standardization. This also comes under pre-processing only. Pre-processing the data is nothing but before you feed the data into the model or your classification or ML algorithm, basically you want to clean it. So that's what basically it's cleaning. Pre-processing means. And then fourth one is about parts of speech tagging on any textual data. So parts of speech is nothing but, let's say you have a sentence like, uh, I like apple. So here like is verb, apple is object, I is object, apple can be a noun as well. So you have these tags, right? Parts of speech, those tags. So we want to do that automatically using some algorithms. So that's what parts of speech tagging also means. So this is also comes under kind of a pre-processing at the same time. Basically, uh, pre-processing is an intermediate step, and then next step is POS tagging in most of the cases. So you can't directly like use POS anywhere, but it will be useful when you are doing some classification or clustering. It will be useful for you, to perform well. That means the accuracy can be improved by doing parts of speech. And then we will do the topic modeling, which is also one more important topic. And coming to text representation, we have TF IDF and word to vec. And coming to text classification, we have naive Bayes classifier here. and then support vector machine classification here. 10th one is convert text to vectors. That means basically representation only, and apply question similarity to provide closeness among the two tests. So yeah, actually this experiments are very well designed. So coming from the basics, we are covering regular expression under basics, and then for the pre-processing step we have one or two experiments, and then representation we have three four experiments, and we are covering some classifiers such as naive Bayes classifier, support vector machine classifier in uh, you know um, text as well. So yeah, this is very well designed. So we'll jump into the first. I'll keep this here. Yeah, I'll keep this here. We'll see like one by one. So here I have the codes. So first is noise removal. Yeah, this is your first experiment. So all these explanations and codes I'm providing, I will provide the codes also to your respective HOD, Ramakrishna Garu, and also you can actually go through this. Like right now, I'm using Collab, so I hope you know how to use the Collab as well. So the basic advantage in Collab is that you can keep both your explanations and code. This is your explanation, right? And as well your code also in the same file basically. So everything can be kept in the same place. So while teaching, this is very helpful because you can have both images, everything, basically images, even text, everything can be, and code also in the same place. I would say that you also start using Collab because it's very easy first of all, and also they will provide some GPUs as well. So here we have T4 GPU. So maybe now you don't need any GPU, but once you go to your third year or fourth year where you have to work on neural networks, deep learning. So there we will use GPUs. So like whatever the experience that we are doing, it is very simple. Simple in the sense, not concept wise, but to run, like to experiment with. If we have one laptop, in that laptop also we can do all these experiments. But once you learn these advanced topics, so you might have to use GPUs. So like in deep learning you would need GPUs. Not every laptop will have a GPU, right? So we usually have CPUs like 4 cores or 8 cores based on your i7 or i5 or something. So better start using Collab right away, because anyways eventually you will need this. You would need to use Collab in your third year or fourth year. So I would recommend to to start using Collab itself. uh, yeah, so that's one thing. So now the first experiment. So we will, like, yeah, regarding the timings, maybe we will from until 12 we will continue, and after that either 1 or 1:30 based on your availability we'll start it. And then I think you will have buses starting from 4. Today we'll end the session by 4. Like I'll try to cover 10 experiments mostly. The rest of the two experiments will take 1 hour later on Monday or someday. We'll cover that one day, like 1 hour session later. But yeah, now let's jump into the first you know uh, experiment. Demonstrate noise removal for any textual data and remove regular expression patterns such as hashtags from the textual data. So understand this. uh, the keywords here are noise removal, textual data, hashtags, right? So usually what happens is you'll get data, right, from the, let's say you joined in a company, and that company is actually, working on social media. So you know how the tweets are, right? So most of them are junky. That means, like there will be a lot of noise. Sometimes we'll use hashtags. For example, IPL is going on. So whenever somebody is tweeting, they'll add the hashtags as, hashtag IPL, hashtag IPL 2024, IPL, or some SRH, something. So team names. So they will add these hashtags. So sometimes we don't need it. We don't need all these tags. So those are called, words are basically some textual data which is not relevant is called noise. So in this experiment, we want to remove those hashtags from the text data that we have. So for that, we will use regular expression. Regular expressions, uh, like you can consider these as formulas or patterns. Formula is nothing but, pattern is nothing but, you define a structure in some way, and then when you are setching it, based on the structure, we will, try to identify if something is there or not. We'll get to it. So regular expressions are often abbreviated as regex, or regular expressions are powerful tools for pattern matching and string manipulation. They consist of patterns which are sequence of characters that define a search pattern. So the regular RE library in Python is the standard library module for working with regular expressions. So this RE library, so regular expression library, this is, it provides functions and classes for pattern matching and string manipulations using regular expressions. So yeah, so how do we use this RE? So basically, what is library or module? So basically, let's say you want to sort some numbers from 1 to 2, 1 to 100 or something. Randomly, I gave you some numbers like 100, 50 numbers. So these 50 numbers, you want to sort it. So what you can do is, you can write a program to write entire thing, the sorting algorithm. For example, you want to sort this using bubble sort. You know bubble sort, right? In your C, either first year or 2-1, you must have learned this bubble sort. So this bubble sort, you will start writing the code, and you will execute it and everything, but it will take a lot of time for each and everyone to write the code, right? So let's say I wrote some bubble sort code. So can you use it? Like, I have the code with me, can you use it? So how do you share the code to somebody else? So that's where comes the modules or libraries. Basically, you don't need to repeat everything, right? So if it is a standard algorithm like bubble sort, you don't need to write it from the beginning. The codes are already available, but how do I share it and how do I validate it? So that's where this comes, libraries and modules. So library or module in Python is nothing but, like, let's say, actually there are developers in open source community. They will write the code and they will create a library or module, and that module will be, validated by many people, and they'll say, okay, this is correct, this is wrong, this is bug, and they'll raise the bugs, they'll correct the bugs. So as a community, they will improve the code. Community is nothing but, like, let's say, even we are part of community of Python actually. If you start using the Python libraries, you are actually community, but you are a consumer. But actually, you can write your own code and also publish it as a library, and then I can use it. So so that is the concept of library. So somebody else can write bubble sort algorithm and then keep, publish it. Publishing is nothing but, you add a module in Python. Those who want it, they will import it. See, this is what importing means. They will import it and they'll use it. So similarly, for regular expressions also, some community or some fellow wrote all the codes, and kept that under the module RE, and then we are importing that, and then that module has all these functions. So using regular expressions, we can search some pattern, we can match some pattern, we can find all. So searches for the first, you know what, I'll directly jump into the, uh, yeah, maybe this is a simple example. So this is import RE, text equal to hello world. This is a sample text. And within this, you define a pattern. Pattern is your hello. So you want to check this pattern if it is there in the text or not. So for that, you have a function re dot search pattern comma text. So this pattern here, this is the pattern and text, and this is your text. So this search function will take two arguments. What is the pattern that you want to search, and what is the entire string where you want to search. So it will take it, and if there is anything that it finds, it will give match as one. If it doesn't find anything, it will return 0. So match will be 0. So in if condition, if match is equal to 1, it will be like, pattern found, otherwise pattern not found. So this is a simple example. Uh, let's actually run this thing. So much time. Yeah, pattern found, hello, is there. Let's say you remove one L and see if it works. Pattern not found. So this is what it is. Now you understood the basic, like how everything like works. Basically, you have a pattern, and you like what you want to set is a pattern. Where do you want to set is a text. Uh, Instead, hello is a, we can search. So pattern found. So here is a, we are just defining it, something like this. But let's say you want to search if there are any characters like T T T. T is there, people tree is there. But you can't always search like this, no exact word. Sometimes your requirement will vary. For example, you want to search uh, a word followed by a digit, right? Let's say you want to search some username, user 123. So you want to find all the users. So it can have, I'll write it, user 123, user 456, user 789. And you want to find if there is any word uh, with user followed by some digits. So how do you, like, you can't always rely on this user one to, like, you can't always specify, no, user 123 if it is there, user 456 if it is there. You can't find all the combinations. Let's say there is user 347. You can't imagine writing all the combinations, right? So that's why we have these patterns. So where you can specify, so first user should be there, and then for digits you can write a formula, a pattern which contains, which represents any set of numbers. we'll see this. So these are the basic patterns you can see. Literal characters. So A pattern A matches with character A. Okay, that's fine. Match any character within this set. So pattern ABC, but within the square parenthesis. So matches either A or B or C. So it will check if there is any A in the text, if there is any B in the text, if there is any C in the text, right? So we'll search that only. Most likely it will be there because ABC are. See, pattern A is there. So yeah, probably B is not there. C is not there. Yeah. And then you have quantifiers. So pattern A within the braces 2 comma 4 matches AA, triple A, 4A. So you can write this. Earlier we wrote TTT, right? T in the brackets. I can mention 2, or actually this will search for TT only. If I mention 3, it will repeat 3 T's. If I mention 1 comma 3, it will, okay, now mash. So it is only returning one group. Otherwise, we could get like 1, 2, 3, everything. If T is there, TT is there, TTT is there, we can search that as well. Another is anchors start only in the beginning of the line. So like start something will write. So this line is starting from hello, right? So that's why this character, if I'm starting from like it will set only in the beginning of the sentence. Let's say this is, let's say we will search for is. So, but even though is there within the string, but it is not showing, pattern not found, because we are saying using this character, this is should be in the beginning of the sentence. So that's what this this anchor start means. Similarly, match one of the several patterns, cat and dog. If cat can be there or dog can be there, something like that. Wildcards. Match any character or set of characters. Pattern. This dot matches any single character except new line. So here dot means anything. It can be anything. Let's check this out. He dot dot. See, hello is there. So here dot means it can be anything. So if I write H some A, let's see what it finds. See, HE AA. So here, let me. Okay. This is only searching actually. If I say find all, let's see. Yeah. Now you can see we have this pattern. Hello, like he dot dot dot, and then found all the matches and and we are printing all the patterns here. So earlier we tried T, right? T 1 comma 3. Let's see if we will find, yeah, 1 comma 3 we found. So that's why we have everything now. 2 comma, yeah. And also you can search for user as well. Maybe we'll get to this after. Uh, so group multiple tokens together. This is grouping. AB plus matches AB, 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 AB. So this can be, there can be many things, right? So that's why we have this. And then we have this one, same T comma 3 and everything. So we will see like what exactly, now you got the basic understanding of it. So we'll go to the actual problem and see, demonstrate the noise removal for any textual data and remove regular expression patterns such as hashtag from the textual data. So for that, we have this code, this entire thing. So original text is this: excited to start NLP project. User one, check this out, cool website, some example.com, and email at this. So this is your original text. And we want to clean this. How do we clean this? We remove the hashtags first. Hashtag NLP, we want to remove it. And we want to remove this user one, which is like when you're tagging somebody, you will use this at the rate symbol, right? So we want to remove these user names, and we want to remove URLs, and we want to remove email IDs. So once we remove those, this is how the clean text will be. Excited to start the project. Check this out, cool website. Now you don't have any URLs, you don't have any user, and you don't have any email ID also. So for this, we'll write the code now. So hashtag patterns. First, we want to see how we can, write hashtags, hashtag NLP, right? So the pattern for this is hashtag /W plus. So here we will see hashtag hash matches hash, I mean like hash character literally, This one, \w plus matches one or more word characters like letters, digits, underscores. This ensures that hashtag contains at least one alphanumeric character after the symbol hash. So yeah, we'll see this here maybe. It identified hash narrate here using this pattern. So similarly, we have email pattern. How does emails look? Example email equal to email at the rate of example.com. So maybe you know what, I'll take this first and write here, and then I'll write Naren. See, it found out NAR. What's the email here? Within this text, what is the email? So it found that, and this is the pattern. So how this pattern works is simple. So you usually have these things, no? At the rate should be there. If it is an email, definitely there should be at the rate. So before at the rate, there can be any name. That name can have letters, numbers, underscores, special symbols, anything before that. So after at the rate, you want to have some name again, but it won't have all the symbols. It will have gmail.com. It can't have uh, any special symbols like hashtag or anything, right? So these are all the symbols that you are allowing here, and here you allow only this hyphen and dot and all. So here you have it, and then you must have dot definitely. So we have dot here, and after dot you should have at least two characters like this can be .com or .in or anything, right? So that's why we say there should be two characters at least. So this can be mentioned here. So yeah, this part is related to two characters. So this is how an email looks like. So for that we wrote a pattern, and we found like we can write another example maybe. Suresh 123 at the rate of KIET dot in. See, it found the other email as well. Suresh123 at the rate of kite dot in. So how it works, we'll see. First, this slash b is there, no? So the slash b is a word boundary, ensuring that all email address is not part of the larger word. So this part and then this part. So this part means matches one or more characters A to Z or A to like small letters, capital letters, and that can be part of an email address before at the rate symbol. So that is this. So this plus means right? So here we understood plus means it can be any number of characters. And the at the rate symbol should be there. And again, match one or more characters that can be part of the domain name after at the rate symbol. So here I wrote kite or Gmail, right? So even that can be it's a domain name. So for the domain name, uh, just a minute. yeah, for the domain name, we won't include this percentages, pluses and everything. So that's what it is here. And then later after the dot, like this is the, like here we have escape character. Dot is we are using it for another purpose. So we will use escape character backslash for that, A to Z, and then this tells you that matches two or more characters or two or more letters, uppercase or lowercase, representing the top level domain ID, domain of the email address. So, and again we have slash b, which matches the entire word boundary. So this is for email. So similarly, we have a pattern for URL as well. In URLs, we have HTTPS and www dot, and then like I will explain maybe from here. This is the URL pattern. So slash b you already know, which matches the word boundary. So this is where the text ends. So that's what it says. That means there should be space after this. So here it says that matches either HTTPS or www dot. This matches that. And then slash s plus matches one or more non-white space characters. So other than space, you can have anything, any character followed by HTTPS or HTTP or www dot, representing the domain name and additional path and query parameters in the URL. And then finally you have slash b. So this is what URL pattern is. And then again we have mentions, right? First we have hashtags here. Similarly, we have mentions also, like hashtag, instead of hashtag, we will have @ symbol. So this is mention. So these are the patterns. So this is the code for it. So what we write is, this is the text first, and then this is the clean text. Remove noise function we are using. In the remove noise function, what we are doing is, first we define the patterns, and then re.sub. What this sub will do is, so this is the pattern, and this is your like how do you want to replace it. So here we are replacing it with uh, empty string. Instead of empty string, you can have anything. Let's say star 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 always. So if we print this now, so yeah, all hashtags, users, everything replaced by star star star. So usually when you are cleaning it, you want to keep it empty string. So that's why it is only quotes. So if you run that, they'll simply remove the hashtags, URLs, email IDs, and mentions. So this is what denoising using regular expressions mean. So yeah, we have completed this first experiment. We'll go to the next one maybe. Yeah. Where is the second one? So the second experiment is perform lemmatization and stemming using Python library NLTK. So I have a code somewhere. This one. So yeah, lemmatization and stemming will perform in this experiment. We'll see what is lemmatization, what is stemming now. Lemmatization involves reducing the words to their base or dictionary forms called lemmas. This process takes into account the context of the word and its part of speech to ensure the accuracy. Lemmatization aims to transform inflected words into their base forms making it easier to analyze text by grouping together words that have the same meaning. For the word, let's say you have running. Okay. That running will be converted to run. So in your text, if there is any running word running, that will be converted to run. Ran, something like ran also is there, and then that will be converted to run as well. So we call these as words, and then root words are lemmas. Similarly, mice would be lemmatized to mouse. Lemmatization requires access to lexicon or dictionary, as it needs to look up each word to find its lemma. Lemmatization is generally slower and more accurate compared to stemming. So we have two methods. So basically, basic idea is that, let's say in your text we have multiple words which are very similar. Let's say running is there, run is there, ran is there. So we want to treat all of these as a single word, because computer doesn't know, right? Running is equal to run. It's just like similar meaning. So that's why uh, we want to perform this operation where we convert everything into similar words. Like all the words related to run will be converted to run. All the words converted to all the words like dogs will be converted to dog. Dog and dogs will be converted to dog only. So we want to find the common word, and we use that common word only everywhere. There are two ways. One is using dictionaries, and another one is using stemming. So in the stemming, what we will do, we'll simply chop off, let's say ing. Like every continuous tense will have ing, right? So we will have these words like extra prefixes or suffixes. We can simply remove those suffixes, and running will become run, right? uh, just a minute. So yeah, with this running will become run, but mouse will be mouse only in stemming. But in lemmatization, mouse will be sorry, mice will be converted to mouse, because it's a plural thing of mouse. Stemming involves removing prefixes and suffixes from the words to obtain their root or stem. This process relies simple rule-based algorithm to chop off access without considering the context of the word. Stemming aims to reduce the words to common base form, which may not always be valid word in the language. So here, running will become run, that's fine, but better will become better. There won't be any er, bet. So after stemming, sometimes we will get words which are not actually meaningful, but in lemmatization, that better will stay better only. It won't become any lesser. Stemming is faster, less resource intensive process compared to lemmatization. Stemming may produce words that are not valid or meaningful, as it applies general rules without considering the linguistic context. But lemmatization involves reducing the words to their base or dictionary form called lemmas. The process takes into account the context of the word and its parts of speech, POS, to ensure the accuracy. Lemmatization aims to transform inflected words into their base forms, making it easier to analyze text by grouping together words that have the same meaning. So basic aim is, you have words which have the same meaning. We want to convert all these words, different forms of the words, into single form. Basically, kind of normalization only. So that's the objective. We can do it using lemmas and stemming. This is the code. So this is the here we will use for lemmatization word net lemmatizer we will use. For stemming we will use porter stemmer. For tokenizing we will use word tokenizer. So in like NLTK is a natural language toolkit. So this is also a library. So using this library, we will do stemming and lemmatization. Like basically, this library has everything that is related to natural language processing (NLP). So the in this library, for stemming purpose, you have porter stemmer. For lemmatization purpose, we have WordNet lemmatizer. So yeah, lemmatize. We are initializing here WordNet lemmatizer. We are initializing here stemmer. We are initializing. So this is a sample text. The cats are chasing each other in the garden. Better mice. Let's convert this into a proper text. They're in the garden and moving faster than mice. Actually, instead, the cats are chasing mice in the garden would be sufficient. So yeah, this is the text. First, we'll tokenize it, convert that into tokens. So for each token, we will apply lemmatizer and store it into lemmatized words. Similarly, we'll apply stemming and store it into stemmed words, and we'll print these things. So this is the actual text. The cats are. I'll print the actual text as well. So the cats are chasing mice in the garden. That is the actual text. So the cat. See, in lemmatization, cats became cat. R is same. R chasing became chasing only. Otherwise, let's print stemming first. We'll understand better. So the state stem. So cats became cat. R is same. Chasing became chase only. Mice is still mice. In is in. The same. Garden same and dot is also same. Lemmatizer words are like the is there, cat is there, R is also there. So here chasing, the chasing remained same. It didn't become chase. It still is chasing. Mice became mouse. Why? Because the cats and dogs. Here cats became cat because from plural it became singular in both. By removing s, stemming did removed like it just removed yes, so it became okay, fine. But in mice, it was not able to identify that okay, it is plural of mouse. So, but lemmatization is able to do it. So lemmatization converted this mice into mouse. Similarly, rest of the everything is same. So you understood the difference. So in stemming, what we'll do is we'll just chop off endings ing, ing, er, ed, these kind of words, no, these kind of suffixes, which are usually like very common. So that is a rule based thing. So that's why when you remove those kind of words, sometimes we will get not so meaningful words. But in lemmatization, we will use dictionaries. So in dictionary, we will see, okay, mouse is there or mice is there. So what is the root word for it? Mouse. So using some dictionary, lemmatization will happen. But uh, like for lemmatization, you need a dictionary, right? That is external source. So that is a burden on the developer. You have to keep dictionary somewhere. And also, it is very time taking because you want to compare everything, right? So if mouse is there in your dictionary or not, something like that, you want to compare it. So that takes time. Even though it takes time, it is accurate. But stemming words, it won't take time. It is okayish accuracy. It will give you okayish accuracy. So this is what stemming and lemmatization means. So we'll move to third experiment. Demonstrate object standardization such as replace social media slangs from a text. So we want to remove social media slangs from a text. So that's our third code. So this is what the third is social media slangs such as lol. You usually use it no in your texting or comments and all. So lol is for laughing out loud. OMG is for oh my god. Have permitted online conversation offering quick and efficient ways to convey emotions, reactions, and thoughts. While convenient within the context of social media interactions, these slangs can pose challenge when we encountered in the formal and professional settings, where clarity and precision in communication are paramount. So basically, what we are saying is, in social media text, if it is there, it's fine. But if it is a formal text, we don't want to have this kind of abbreviations like lol, OMG, BRB, BFF. So this we don't want these shortcuts. We want the proper text. So this is what we call standardization. In this task, we aim to address this challenge by developing Python script to standardize the text by replacing social media slangs with their corresponding standard phrase or expressions. By automating this process, we can ensure that text derived from the social media sources maintains clarity, professionalism, making it suitable for various applications such as customer support, academic writing, and business communication. So this is the code. First, I'll explain what is the input and output. Our input is original text, lol, OMG, BRB, TBH. This is hilarious. So this is the comment that you found in some social media comment. And uh, why it is standardized replace. So this is your text, and in your original text you have lol, omg, brb, tbh. This is hilarious, and we replace lol with laughing out loud, omg with oh my god, brb with be right back, tbh with to be honest, and this is hilarious is anyway there. So we want to remove this character, like uh, extra slang words from the text. So what we do, first we'll take the replace slangs is the function we have defined for this purpose, and we are maintaining a slang dictionary. So this we have to do it manually. So if what is the meaning of love, so laughing out loud. So like this we want to create a dictionary somewhere and keep it with us. And first we'll send the text and the dictionary to this to this function. What we will do, first we'll split this text based on the white space. Then we will become it will become uh, I'll print the words as well. Words in the text. So these are the words in the text. And after that, we will convert this into lowercase first. Let's say in the text we have capital LOL. So this capital LOL will be converted into lowercase first. Once we have lowercase, and then we will check in the dictionary if that lowercase word is there in the dictionary or not. If it is there, we'll simply replace that text with new text, slang, dictionary value. So we will replace that with this. If it is not there, we'll simply add the same word. And finally, we'll join everything with the space and return the final text. So that is what here we have done. So you understood, right? So first we'll take the text, split it into words. How would you do it? First we'll take the text based on the space. So here we have space, right? So based on the space, we'll split the text into words. So finally we will get this. Once we split that, we have words, and the word will be converted into lowercase. Once we convert that into lowercase, and then we'll check if that lowercase word exists in our dictionary, slang dictionary. If it is there, we'll replace it. If it is not there, we'll simply keep it. For example, uh, hilarious. Hilarious word is not there in the slang dictionary. So that's why we kept it as it is. So this is what standardization means. So basic idea is that you have your data, you have your mapping basically. Lol means this, BRB means this. So you keep this in a dictionary. You get the text based on the space, you split it into words. So replace the words if it exists in the dictionary or not. So it's very simple actually. So we finished 3 experiments now. We have 2 more to cover in this half an hour. Let's see. Now we'll do POS tagging. So perform part of speech tagging on any textual data. So this is one data, like one experiment. Where do you want to do the POS tagging? So we'll jump into it. So we'll do POS tagging here, parts of speech tagging. So let's understand what is POS tagging. In the realm of natural language processing, NLP, one of the fundamental tasks is understanding the grammatical structure of a sentence. So parts of speech tagging is a crucial step in this process where each word in a sentence is assigned a specific grammatical category or parts of speech, such as noun, verb, adjective, adverb. This categorization helps in extracting meaning from the text and enables various downstream tasks such as syntactic analysis, neighbor entity recognition, and sentiment analysis. So basically, the task is POS tagging means if you have a word like your name, then you should tag it with proper noun. If it is like mango, then you name it noun. If it is running, you name it or you tag it with verb, something like this. So, given a sentence, you want to tag every word in that sentence with some grammatical category. So, some of the examples are these. NN means noun, singular or plural, we can say. Dog, cat, table, everything comes under nouns. Eat, run, sleep, these things will become, comes under verb. It is represented as VB. Adjectives, big, happy, green, this will be uh, tagged with JJ, adjective. RB means adverb, quickly, very well. So PRP means personal pronoun, I, you, he. So IN means preposition or subordinating conjunction, like basically prepositions. IN means prepositions. DT means determiner. Determinants are three only: the, a, an. Only these three comes under determiner. VBD means verb, but in past tense. Ate, ran, slept. That is VBD. Here VB means verb base form. So present tense. Eat, run, sleep. But this is in past tense. VBZ, verb third person singular present. Eats, runs, sleeps. So it is verb only, but in a singular, when you refer somebody, in a singular person. So you eat, you use eats. Uh, he eats apple every day. So that eats is verb, but in a third person singular present. PRP dollar means possessive pronouns. Mine, my, your, his, all of this comes under possessive pronoun. So these are some examples. So in our code, we'll see, like I'll execute this code first and then see. Uh, okay, something is wrong here. Okay, I have to do this first. Yeah, this is your original text. I love to eat pizza with my friends. This is your uh, original sentence. And now we converted that into pairs. I comma some tag, love comma some tag, to comma some tag, right? My comma some tag, something like this. So how do we do it? So first NLTK. I think we should go to NLTK website and see, like get the basic understanding. Because in NLP you would use NLTK library, like for everything. Almost every code of yours will have NLTK library. So this is your NLTK library. This is NLTK is a leading platform for building Python programs to work with the human language data. Human language data is nothing but natural language. It provides easy to use interfaces to over 50 corpora and lexical resources such as WordNet, along with the suite of text processing libraries, classification, tokenization, stemming, tagging, parsing, semantic reasoning, wrappers for industrial strength NLP libraries. So all these tasks we can see it, like we can do it. Classification, tokenization, stemming we have done already. Classification we'll do it later. Tagging is nothing but POS tagging also, only. Parsing is like instead of tagging you want to I think, is there an example? Yeah, this is called parsing. So this is a sentence, you want to convert that into hierarchy of tree. So you want to uh, convert that into noun phrase, verb phrase. Within noun phrase, what are the nouns? What in verb phrase, what are the nouns and verbs? So all of this will be, comes under parsing. Semantic reasoning. So all these tasks are simplified using this NLTK library. Thanks to hands-on guide and using programming fundamentals along the fundamental mistakes. NLTK has been called a wonderful tool for teaching and working in and computational linguistics using Python, an amazing library to play with the natural language. Natural language processing with Python provides practical introduction to programming language. So some simple things you can do with NLTK. So one is tokenize and tag some text. So at 8 o'clock on the Thursday morning, Arthur didn't feel very good. So you can first, this is a sentence, right? That sentence need to be split into words. So instead of doing it, like for example, didn't, right? So this can be converted into did not. If you do it using only space, you can't, like this whole thing will be considered as one word. But we know that did and not are two different things. So that's why we have word underscore tokenize. So that will have a knowledge of how to tokenize this word. Did and not will be separate words here. So POS tag. So here we, whatever we are doing right now, that comes under POS tagging. Named entities. So for example, uh, person, Arthur. Mm, So in this text, we have a person name, right? Arthur. So that is identified as person here. And this parsing that is here. So it is complex. We'll not get into this. So these are all the functions, like how to use this module index. So within this, what are all the functions that are available? NLTK data, decoders, all of these are functions. So here for tokenization, we have this many. tokenize.api, tokenize.casual, tokenize.destructive, so tokenize.punct. So we usually use this. And yeah, so this is the basic understanding of the NLTK library. So if you want to work in NLP, it is a must library that you have to learn about. So remember, we used Punk, like we saw Punk there. So if it is not available, we have to download it sometimes. NLTK.download, within the braces, if you say Punk, it will download the library, or it will download the resource basically. So now, coming back to the actual problem, POS tagging. So first we'll take the original text. I love to eat pizza with my friends, and first we'll tokenize it. And once we tokenized, the words will be passed to POS tag. What is POS tag? It's a POS tagger from the NLTK library. So, and then we will get POS tags and print it. So I is PRP, love is VBP. So here PRP means personal pronoun. I is a personal pronoun. Love is a verb present tense, not third person singular. Two is two anyway. VB. VB is nothing but verb in a base form. Eat is a base form, right? Ate is a verb but in a second or third tense. Pizza is noun. With, where is with? In. It's a conjunction. In is a, like, with is a conjunction. My is a personal pronoun, but possessive. Like my, his. We learned this here, no? My, your, his. All of these comes under personal pronoun, but possessive version. Friends, NNS. Noun but plural. Friend is a noun. Friends is a noun but plural. Dot is anyway dot. Period. So this is our POS tagging. So how do we do it? We have POS tag library, or function actually module in the NLTK library. So we imported it first, and then whatever the text we have tokenized it first, using word underscore tokenize. Once we have these tokenization tokens, those tokens will be passed to POS tags, and we'll finally have POS tag here. Yeah. So this is it for fourth experiment. We have 10 minutes. We'll complete the fifth one. Okay, this is little complex, but we'll try to cover. So LDA means latent Dirichlet allocation. So this is very complex mathematical, algorithm for topic modeling. We don't get into math now. We will only use. We'll see how we can use LDA, because, like I said, we don't need to learn all the math and all of that, because somebody already wrote the code and it is available to us. So that's the advantage with these libraries, because like not everyone can understand all of the math, no, but still we should be able to run the code. So yeah, first let's understand what is topic modeling means. Topic modeling is a type of statistical modeling used to uncover the latent topics or themes present in the collection of documents. It's a form of text mining or natural language processing technique that aims to automatically identify the topics within the large corpus of the text. So it means, let's say you have documents, like you have a like newspapers from last 1 year. For every day you got a newspaper, and each newspaper is in your digital mode. like text, and you want to see what are all the topics that last 10 days, let's say we'll take only last 10 days newspapers and see in the last 10 days what are the topics that are there in the news, right? So this is the problem statement. How do we do it? Automatically. So that's the problem. So you have 10 like last 10 days newspapers which doesn't have any label, like okay, this is business related document, this is uh, politics related document, this is sports related document. This kind of label we don't have. We only have documents. From the documents, how to identify the topics is the question. So that's what we say, topic modeling. So what we do is, okay, we'll take this document. In this document, this topic, this document talks about maybe around 80% of this document is about this topic one. 20% of the topic document is about topic two. Similarly, another document. Okay, 50% of this document is talking about topic one. 20% of this document is talking about topic two. 30% of the document is talking about topic three. Like like this, we have to give the percentages. Okay, there are two tasks. How to identify the topics is one, and once you have the topics from each document, you tell me what is the percentage of the topic. So that's what topic modeling means. The most common approach for topic modeling is latent dirichlet allocation. In LDA, each document is assumed to be mixture of various topics. That means a document contains or talks about multiple topics. Each topic is assumed to be distribution over the words. That means, let's say politics, Narendra Modi is one word, election is another word, vote is another word, government is another word. So under this in this topic, there will be some words, right? So first, from word to topic level, we have to understand, that is, under this topic, what are all the words that occur. And next level is, under the document, what are all the topics we have. So it is a two-level process. The algorithm then iteratively assigns words to topics and topics to documents in a way that maximizes the likelihood of the observed data. So it has two steps. First, it assigns words to topics and then assigns topics to documents. So this is the basic idea of it. Where do we use it? Topic modeling can be useful in various applications such as document organization. It can help in organizing and summarizing large collection of documents by grouping similar documents together based on their topics. Information retrieval. By identifying topics, it becomes easier to retrieve the relevant documents from a large corpus. Recommender systems, content analysis, social media analysis. It has so many advantages actually. How LDA works? Latent dirichlet allocation is a probabilistic generative model used in topic modeling in large collection of text document. It operates under the assumption that documents are represented as random mixtures over latent topics, and topics are represented as distributions over the words. The goal of LDA is to infer these latent topics given the corpus of documents. So basically, it's a very huge algorithm. I'll, I'll like explain it like within few words basically. So let's say you are given a corpus. What you will do first is identify the words. These words will be allocated to topics first. Okay, baseball is related to sports. Catch related to sports. Narendra Modi related to election. Uh, some election vote is related to elections. So something like this. So for each word, we will tag a topic. So, okay, now you have a document, right? In the document, you take each word and identify with, like tag with the topics, right? Let's say in the document, there are 100 words. Out of 100 words, let's say some 30 words are related to politics, and some 30 words are related to sports, and other 30 words are, 40 words are related to sports, politics, and health. These three topics are there. So then we will say there is 30% politics, there is 30% sports, there is 40% health related words in this document. So that's the basic idea. So, like I said, uh, along with the NLTK, we will use GenSim library. GenSim is also a library which is similar to NLTK, and we will use that library in this experiment. First, we'll import everything, and we'll download stop words, this tokenizer and WordNet, everything. Let me run all of this. So these are the so first we have these documents. Sugar is bad to consume. My sister likes to have sugar, but not my father. My father spends a lot of time driving my sister around the dance practice. Doctor says driving may cause increased stress, blood pressure. So something like this. We have some documents. First, we will remove the stop words, and then we will remove the punctuations, and then we will do the lemmatization. So everything comes under this pre-processing. Once that is done, we'll create a corpora for dictionary, and then we have this LDA model, gensim.models.lda model, and we'll pass this corpus, whatever these documents are there, no? So that will be passed to your LDA model. Number of topics is 3, and we want to build a dictionary, and passes is 15. So this is your output. We said we want the 3 topics. First topic has 0.65 this much about driving, pressure, cause, size. So these words comes under topic. These words comes under topic 1. Father, sister, well, drive. This comes under topic 1. Sugar, like, bad, consume. This comes under topic 2. So what we did, we assigned words to topics, and how much percentage of this. Like this topic contains 65% driving, 65% 6% driving, 6% pressure, 6% cause, 6% suggest, something like this will go on until 100. So similarly, 7% father, 7 like 0.72 percent sister, 4% well, 4% drive. Similarly, in each document also, we will see how much percentage each topic is. Here, topic 0 has 4%, topic 1 has 4%, but topic 2 has 90%. That is this. document which is talking about sugar like bad consume, right? So that, yeah, exactly. Sugar consume, bad, all of this, like this first topic is talking about sugar, like this document. So that's why the first document has 90% of topic two. This topic two has sugar like bad and all of this. So this is the uh, LDA model. So you understood the basics of LDA, right? Basics is nothing but first you tag word to a topic, and then you tag topic to document. That's the basic idea. So we are at 12 now. So till 1, we have this lunch break, right? So I'll stop now. We'll continue from 11. Sorry, 1. Is there anybody? Hello? Is there any admin here? Yeah. Anyway, if nobody is there, simply like uh, please go and have lunch. We will start at 1. From 1 to 4, we will have a session covering the rest of the 5 assignments. Okay, okay. Thank you, thank you. Please have lunch. Hello. Admin is there, like everyone has, is in the class. Everyone has come. Like, can someone, send a message whether everyone is ready? Like, shall I start or not? Hello. Okay then. Thanks. Okay, we'll start our second session. Basically, from 6 to 10, we'll cover today. For like basically 11 and 12 are actually related to each other. So it's on the same data set, but different tasks basically. So that we will take 1 hour later. But for today, will like the second section will be mostly about uh, you know text classification or text representation actually. So sixth is about the TF-IDF, which is actually a text representation technique. Word to vec. Second one is about word to vec. This is also very famous text representation technique. Eighth is text classification using naive Bayes classifier and a text blob library. So sixth and seven are about text representation, but eighth and ninth are about text classification. And the 10th is actually like again text representation only, converting to text, like convert text to vectors using term frequency, and apply cosine similarity to provide the closeness among the two texts. So that is actually is nothing but 6 only. Like both 6 and 10 are very related. Okay, we'll see. Like I think first we'll cover 6 and then 10, and then we'll continue with the 7, 8, 9. Yeah. So this is it. So now first let's cover 6. So demonstrate term frequency, inverse document frequency using Python. So one each. Okay. So first we have to see what is text representation actually. So like in machine learning, like NLP is part of machine learning only, right? So we can't always pass our words. Like machine learning algorithms only understands numbers basically. You can't give words or letters to it. You are supposed to convert everything into numbers. So how do we convert, like what are numbers? Number is like one number is one scalar basically. If you have two numbers, we call it's a vector, two or more basically. Then we call it a vector. If we have multiple vectors, that means rows and columns both are there, then we call it matrix. After that, we have tensors. So it starts with the numbers start with scalar, which is nothing but one number. It can be positive or negative or zero, it can be anything. After that, we have vectors. Vectors is nothing but For example, you want to represent some person by height and weight. Height is a number, weight is a number. So that vector represents one person. Yeah, there was some disturbance. Yeah, fine. So yeah, so like how do you, like if you want to give a number or say something, like how much is somebody is waiting, like what is the time, you give a number, what is an then if you want to represent somebody, you want to represent them by attributes, right? So you would say that okay, this guy is 5 feet 4 inches and some 60 kgs. So that 5.4 comma 60 are numbers, but two numbers which we call a vector. So one vector can represent a person, like any object basically. It can be a car, it can be a person, it can be anything. Let's say you want to represent a group of people, like a class of people, like your whole class. If you want to represent it, what you would do, you put your attributes as columns. Like columns will be height, weight, roll number, class, section, something like, right? But in rows, you will have all the people are your students. So student 1, student 2, student 3, student 4. So that will be your rows. So you are able to imagine, right? So rows will be corresponding to students, columns will be corresponding to the attributes of the students. So height, weight, age, date of birth, marks in some subject 1, subject 2, subject 3, something like this. So this comes as matrix. If you have multiple such matrices, like for example, multiple classes, like not just your class, multiple classes are there, and then you want to represent it, then we call it tensor. So everything, like uh, I can't describe you in words, right? Okay, this person like has height of this many feet, and 60 kg he weights, and he is from class A, and his roll number is this. Everything that I can't give it to the machine learning algorithm as a paragraph. That paragraph needs to be converted into vectors. Only then it will be able to understand. So that's the basic requirement of any machine learning algorithm. What is converting your knowledge into numbers is nothing but representation. Representation is nothing but vector representation. So you convert everything into vectors. So coming to text, we call it a text representation. What is text representation? Simple. You convert your text into numbers or vectors. That's what text representation means. So how do you convert it? What would be the best way to convert it? And how do you evaluate it? All of this comes under, after that, like comes under the text representation. So now we'll go through what is text representation. So text representation in the context of natural language processing refers to the process of converting your text data into a format that can be easily understood and processed by the machine learning algorithm or other computational models. The goal of text representation is to capture the essential information and characteristics of the text while discarding the irrelevant details. So that's the main point here. The goal of text representation is to capture the essential information. Basically, you have paragraphs. Sometimes some sentences might not make sense, and sometimes some words we don't even need some words. We should be able to pick the right words or the important words and ignore irrelevant details. That's what this text representation means. That's the basic goal of it. There are various techniques for text representation, each with its own advantages and limitations. Here are the some common methods. So bag of words is one method. Term frequency, inverse document frequency is one method. Word embeddings is another method. N-grams is another method. Topic modeling. So you remember, like in the morning session, we discussed LDA for topic modeling. So that is the fifth point. So all of this except four, we will cover all of the points in this session. So bag of words. In bag of words representation, a document is treated as collection of words and the frequency of each word in the document is recorded. This results in numerical vector where each element represents the frequency of specific word in the document. Bag of words discards the order of the words and focus only on the presence and the absence of the document. It is simple to implement, computationally efficient, but lacks semantic meaning and context. I'll try to find some image. So this is an example. The child makes the dog happy. That's a document one. The dog makes the child happy. That is document two. Now, how do we represent these two sentences? Right? So, what we will do is we'll count how many times the occurred, how many times dog occurred in this sentence. Once, makes occurred one time, child occurred one time, happy occurred one time. Similarly, the dog makes the child happy. The occurred two times here and here. Child occurred one time, makes occurred one time. So dog frequency is one, happy frequency is one. Now what we will do is we will first create a vocabulary. Vocabulary means what? All the words that are there in the all the documents, right? So that's what we call vocabulary. So you combine all this. The dog makes child happy, and here also in document two also, if there is any, like in this case we have same data, but if you have multiple documents, different things will be there. So all of them will be columns now. In the rows, what we will have something that we want to represent. We want to represent the documents as numbers. So that will be rows. So now what we will do is in document D1, how many times child occurred? That is one time here. So at the same time, how many times dog occurred? One time. Similarly, we'll count everything. The occurred two times, the occurred two times. So this will be your bag of word representation. 1 comma 1 comma 1 comma 1 comma 2. So that is document D1 and the document D2 is same. But if you observe, like here we wrote this bag of word. Time to edit this. here. Bag of words discards the order of the words and focus only on the presence of the absence of the document. So here two sentences are different actually. The child makes the dog happy, the dog makes the child happy. But what we got was same representation for both. Why? Because the bag of words does not care about order of the words. So which word came first, which word came later, it doesn't matter to it. It will just count, take the count of each word and keep it in the vector. I'm getting another image. You will be able to see. So this is another thing. Small dog, cute cat, cute dog. So these are three documents that can be converted into 0011, 1200, 0110. Cat, cute, dog, small. These are the words vocabulary, and correspondingly D1 is this, D2 is this, D3 is here. So here you can see the representations are different for D1, D2, D3 because 0011 is one, like document 1, 1200 is document 2, 0110 is document 3. This is different because each have different words actually. But in this case, we see both the documents have the same words. Even the order changed, the representation turned out to be the same. So this is what we call bag of words. Now we come to TF-IDF. TF-IDF calculates the importance of the words in the document relative to its frequency in the entire corpus. It considers both frequency of word in the document TF, that is term frequency. Frequency of the word in the document is TF, and the rarity of the word in the corpus, IDF, like inverse document frequency. How many times the word, how many documents the word occurred in. That is what we call DF. Words that are common in the documents but rare in the corpus are given higher weights, while common words across the documents, that is stop words, are given lower weights. So if a word is very common, like it occurs very frequently in all the data, like for example, if you write any English poem or like any English text, you will usually use a, the, is, are, of, these kind of words, right? So we actually don't understand like what is the importance of this. So if you are talking about politics, you want to hear words about government, vote, Narendra Modi, election, something like this, right? These are important words. But is, are, the, these are all not important. Let's say, like I didn't give you the topic. If I just say election, Narendra Modi, vote, you will say, okay, I'm talking about politics. But if I just say that, okay, am, is, the, then you won't be able to guess what I'm talking about, right? So because they are very common to all the topics. So based on the words, you won't be able to say what I'm talking about because they are very common to all the topics that we can think of. So that's why we call those words as stop words, which doesn't have any meaning. So what we want to do is, here we gave everything same weightage, right? Instead, we want to reduce the weightage of these, like for example, here, it occurred in both. So we want to reduce the weight of but increase the weight of dog and child and happy. So important words should get more weight, unimportant words should get lower weight. That's the whole idea. So how do we do it? I'll show you the procedure. First, I'll get an image to represent. So this is the formula for TF-IDF. So weight of a frequency of X in Y. X is the word, Y is the document. W of X comma Y equal to TF. That is term frequency of X in Y into log of number of documents containing X, DF. That is DF. N is total number of documents. N by DF log of. So this is the TF-IDF formula. So earlier what we did was, in bag of words, we considered only TF. But in TF-IDF, we consider both TF and then IDF. Here IDF is nothing but log of N by DF. And then we have word embeddings. Both bag of words and TF-IDF are statistical methods. So based on counting, they'll represent some documents and everything. But the problem is the vocabulary size. If the vocabulary size is increasing a lot, then the vector representation will be very high. Let's say you have 100 documents. In 100 documents, we have 50 words, new words. Then we'll have 50,000 new words. Basically, our vocabulary will contain 50,000 words. So 50,000 words is too much actually. Like very long, 50,000 elements will be there in the vector. Very long vectors we will get. So that's the problem. So if you have too long of vectors, then it is very hard to process, because it will take a lot of time to process all those 50,000 entries. So that's why we'll simply use the neural networks. What it will do is, it will do the dimensional reduction. So that 50,000 will be converted into just 300 dimensions. So with the lower dimensions, we will be able to represent a lot of information. So that's what we call word embeddings. Word embeddings are dense vector representation of words learned from the large corpora using techniques like word-to-vec, glove, and fast text. In word embeddings, each word is represented by a fixed size vector in continuous vector space, where similar words have similar vector representations. Word embeddings capture semantic relationships between words and can preserve contextual information. They are widely used in NLP tasks such as text classification, sentiment analysis, and machine translation. So this is what word embeddings mean. We have n-grams and we have topic modeling. We covered anyway previously. Now we'll come to the actual problem of this TF-IDF. Why I explained all of this is because in NLP this is very important to learn about bag of words and TF-IDF. Along with it, anyway, our next experiment is about word to vec only. Even for that, we'll need some context, right? So we actually covered what is text representation basically. So yeah, now we'll go in detail about TF-IDF. TF-IDF, which stands for term frequency inverse document frequency, is a statistical measure used in natural language processing and information retrieval to evaluate the importance of a word in a document relative to a collection of documents known as corpus. It's commonly used in tasks such as text mining, document classification, and search engine ranking. So here term frequency measures how frequently a term word appears in a document. It is calculated by counting the number of times a term appears in a document, normalizing it by the total number of terms in the document. The idea behind TF is that more often a term appears in a document, the more important it is to that word document. The formula for calculating TF for a term T in a document D is number of times term T appears in document D by total number of terms in the document. So it is like probability. The document will have, let's say, 100 words. Out of 100 words, how many times a word occurred? So that will give you term frequency. Similarly, we have inverse document frequency. Inverse document frequency measures the rarity of a term across the entire corpus. It's calculated by taking the logarithm of total number of documents in the corpus divided by the total number of documents containing the term, and then adding 1 to avoid division by zeros. So basically, if a word did not occur in any documents, it will be 0, right? The count will be 0. So we can't divide any number by 0. So simply we will add +1 just to make it mathematically, stable. That's it. The idea behind IDF is to scale down the importance of terms that appear frequently across many documents and scale up the importance of the terms that appear very rarely. So if a word is rare, that is, if it is not occurring, in many times, then will take that as uh, important word. If a word is occurring very frequently, like as, the, and all of this, then we treat that as very frequent word, and we won't give much of importance to it. The formula for calculating idea for a term T in a corpus is IDF is log of total number of documents in the corpus by total number of documents containing the term T +1. So this is the formula. So TF-IDF calculation is TF-IDF is calculated by multiplying TF of a term in document by the IDF of the term across the corpus. The result is a measure that reflects both importance of the term in the document and the rarity of the term in the corpus. The formula for calculating TF-IDF for a term T in a document D is this: TF into IDF. In summary, TF-IDF assigns higher weights to the terms that are frequent within the document but rare across the entire corpus. This helps in identifying terms that are important and relevant to the particular document while filtering out common terms that appear across many documents. TF-IDF is a fundamental tool in the text analysis and information retrieval, often used for tasks such as document tracking and text summarization and content recommendation. From SKLN, so this is the whole theory part of it. Now we will see what is the how we would represent, like how we would code it. So TF-IDF, we have sklearn, right? Scikit-learn. So in that we have all the NLP related TF-IDF bag of words. All these methods are available in Scikit-learn, sklearn basically. So first we imported it, and then now let's define the documents, sample documents for on general topics. So the universe is vast and mysterious. Ancient civilization left behind fascinating ruins. Climate change is pressing global issue. Artificial intelligence is transforming various industries. Healthy eating habits contribute to overall well-being. Similarly, like this, we have some 10 documents. So first step is to initialize the TF-IDF vector model. So we imported it right here by calling, because everything is a class there. By calling this, we'll create an object of TF-IDF vectorizing. Now we have initialized, we should learn how to use it. So this is the object. In the object, we have functions fit underscore transform, and then we have another feature fit get feature names out. So this is the TF-IDF matrix. This is the feature names. Feature names are nothing but our vocabulary only. Let me actually print this first. Let it run. Right. First, we are printing TF-IDF matrix. So this is how the data looks. So 0th document, 37th vocabulary. Otherwise, first let me get this features as well. So this is the vocabulary. So we have 10 documents, right? All the 10 documents combinedly will form some vocabulary. Like basically every word that is occurring in this documents. So that is what we call vocabulary. Let's call vocabulary. So this is our vocabulary. Ancient and are artificial, behind, being, change. All these are words that are occurring in these 10 documents. Now we have to represent it using some matrix, right? So even though it is supposed to be a matrix, we'll because there are very few words. For example, this has the universe is vast and mysterious. One, two, three, four, five, six. Only six words are there. So why to use like we will say only 37, 156. This is so zeroth document has six words. So all these words indexes are here. One has this many. So 10 documents will represent everything in this kind of a dictionary or matrix. Actually, this is a matrix only. You can convert this into a matrix. So for visualization purpose, they represent it like this. So now you see it turned into a matrix. Document 1, document 2, something like this. It is as simple as that. The matrix. Now we want to print all the important words in each like document. Document 1. See, if you see here, and is having 0.39. Like, what are the important words? Important words are mysterious, universe, and vast. So they have 0.4 weight, but and is they are getting only 0.3 weightage. You see, so it's the same thing with everything else. So in document 2, ancient behind civilization fascinating left to runes, everything has 0.4. Here is there. Is has 0.3, but change, climate, global, and which are domain related words, they are having higher weights, like is and are. Like these words, they are getting 0.3, which is lower compared to 0.4. Even here, is 0.316. 2 is 0.3 here. So 2 is getting more weightage here. See, half is getting 0.3, but diversity, experiences, human, these are important words, right? So that's why it is getting 0.4 weightage. So this is what TF idea is. So eventually what we did is, first we will get a document, like 10 documents or 20 documents, any number it can be. First, we'll clean it. We are supposed to clean it actually. We haven't in this experiment, but that's fine. It is about TF IDF only, so it doesn't matter much. So the idea is get documents and then convert them into vocabulary and then create a matrix in which each cell will be represented by TF into IDF. What is TF? Term frequency. What is IDF? Inverse document frequency. So these two will be multiplied and then kept in the cell. So that will become our vectors. So once you have the vectors, you can do classification, you can do clustering, you can do anything actually. So this is our sixth. Now actually let's go to 10th actually, because this one is related to TF IDF only, or 10th experiment. Let me run this. So 10th assignment is convert text to vectors using term frequency and apply quotient similarity to provide closeness among two texts. Okay, quotient similarity I will cover also in this. Let me first, you understood what is, like, we'll go through it maybe. Let's see. I So first we'll discuss what is cosine similarity. Then we'll discuss, how to write program to it and all of that. So yeah, we have that corresponding text now. So what is cosine similarity? So let's say you have two vectors in a space. How do you say these two are related, and how do you say these two are not related? So that we will do it using cosine similarity. For example, in the first case, x and y are two vectors, right? So angle is close to 0, that is cos theta is close to 1, then we call it similar vectors. Here, please, look at this. If two vectors are close, then it will be less than 90 or it will be close to 0, right? So angle theta is close to 0, then cos theta close to 1. So cos of 0 is 1, right? So that's why 1. So if cos theta of something, two vectors, is equal to or close to 1, we say these are similar vectors. Angle is 90, cos theta is close to 0, that is orthogonal vectors. So if two vectors are about 90 degrees angle, then we will call them unrelated actually. Why? Because the cos theta is equal to 0. So there is no similarity between them. And then we have angle which is close to 180. Then cos theta will be -1, close to -1. Then we call them opposite vectors. You understood, right? So based on cos theta, we can tell if two vectors are close or not. So angle is close to 0, we call them related. If the angle is about 90, we call them unrelated. But if the angle is about 180 degrees, they're actually opposite vectors. So how do we calculate cos theta? Cos theta has this formula: A into B by mod A and mod B. So this is the dot product. A1 A2 plus B1 B2 plus, A1 B1 plus A2 B2 plus A3 B3 by root of A1 square plus A2 square plus A3 square into root of B1 square plus B2 square plus B3 square. So this is the dot product of two vectors by magnitude of vector 1 and magnitude of vector 2. So that is how you calculate cosine similarity. So now we'll see convert text to vectors using term frequency and apply cosine similarity to provide the closeness among two texts. So these lines, first this is the code. We'll see. Yeah, first we'll import the all the file, like all the important libraries first. We have numpy matplotlib for visualization. And then we have scikit-learn, sklearn. Let me go through the sklearn as well once. So sklearn is also a library. In the morning we talked about NLTK, right? So sklearn usually is about machine learning. So this is also one more library. You will have all kinds of representations here or functions. So one is classification. Next we have regression, and then we have clustering. So within classification, we have linear models, nonlinear models, support vector machines that we will discuss later. In the second or third, like next one or the second next one will be about support vector machines only. All the classifications will be here. Unsupervised learning, model selection and evaluation, all of those are here. I'll do sklearn for so I'll share the link as well here. Okay, this is supposed to be text. So this is the text and like link. You can follow this. So this is what sklearn future TF idea vector complete picture is. So we have analyzer, preprocessor, tokenizers, fit transform, whatever the feature get feature names out. So this will give you the vocabulary, inverse transform. So you have all the methods here. Yeah, that is about scikit-learn. So from the scikit-learn, we have both TF idea vector and cosine similarity. We have these. So now similar to TF idea vector, like last experiment, what we will do is first we'll have documents. This is the first document. This document is the second document, and this is the third one. Is this the first document? So we have 4 documents. The text is like this. So TF idea vector first will convert it to vectors. That is create TF idea vectorizer instance, fit and transform the documents with the TF idea vector. This will create the vectors for all the documents. Calculate the cosine similarity between the documents, because once you have the matrix, anyways you have the vectors, right? So between 2 vectors, what is the cosine similarity? We'll calculate that. And then we have we'll show what is the cosine similarity between multiple documents. So first we'll create 8x6 figure size cosine similarity. This matrix we want to display CMAP equal to grace, interpolation nearest, color bar, cosine similarity between the documents is our title. X ticks. So X and Y axis are filled with documents, and we'll display the matrix. So this is the matrix. So you can see document 1. So anyway, because like in the diagonal, what we will have document 1 comma 1. Quotient similarity will always be 0, right? Or quotient similarity will be 1, because both are same documents only, right? So that's why this is 2 comma 2, 3 comma 3, 4 comma 4 anyway will be black. Black here means similarity of 1. So the range is from 0 to 1 actually. So the documents will be very similar because they both are same. But if you observe, 1 and 4 are also similar. Why? You can see here. This is the first document. And is this the first document? So both are having similar words, first and first, right? So that's why it turned out that these two documents are very similar compared to second. Is this the first document? This document is the second document, and this is the third one. So comparatively, this last sentence is closer to first one for, and then it is closer to second, and then finally it is closer to third. So that's why the colors are like this. So this first document is very close to, like to itself, it will be very close. It is very close to fourth document, then it is very close to second document, and finally it is close to third document. You can see the gray color. If it is black, it like they are completely similar. If they are gray, they are similar, like okay, they are similar but not the same. If it is white, that means they are completely totally different. For example, 3 and 2, it has completely white space. 3 and 2, so these two documents, uh, this document is the second document and this is the third one. So these two are very unrelated, because this is talking about second one, this is talking about third one, and format is also different. Here there is and, there is no and in this, so that's why they are dissimilar. So this is our next experiment. So what we did in this, I'll discuss like what are the first steps. First we imported, first let's discuss the quotient similarity. First we identified, like we discussed what is quotient similarity. If two vectors are very close, that means the angle between them is 0 or close to 0, then the similarity will be very high. Similarly, if the angle is growing, then it will be 0. We understood what is cosine similarity first. Then we imported the libraries sklearn and my matplotlib and cosine similarity, everything. Then what we did, we prepared the documents. So I think I should move this down actually. Yeah, the steps are this. Prepare the document. The lines define list of documents for training. Each document is represented as a string. So create a TF-ID of vector instance first. So this is what, yeah, this is the creation of TF-ID of vector instance. And then finally fit and transform. This line fits the TF-ID of vector as two documents and transforms the documents into TF-ID of matrix. So whatever the documents we have, will pass that as input to this uh, vector, like input to this method. It will convert the documents into numbers. Here the numbers are nothing but matrix. After that, we calculated the quotient similarity between the two matrices. Like both the matrices are same only. So we have to pass two documents, sorry, so two matrices. So we pass both the same, and we'll get quotient similarity. And finally, we visualized it using matplotlib. So create a figure with a specified size, that is nothing but 8, 6. Display the quotient similarity matrix as heat map using grayscale color map. So uh, cosine similarity matrix you give it, then it will identify what is should be the gray color, what should be the uh, white color, one black color, and then we'll set the color bar to the plot for the reference, set the title of the plot, x ticks, y ticks, x-axis label, y-axis label, and finally display the plot. So first we'll say what is the ticks. So whatever this uh, we are having, we can see some ticks here, right? So we set that as ticks. X label, Y label, we documents, we show it as documents, and plot. Also, let's print print. So this is the matrix that you are seeing in the visual, like visually you are seeing here, but the same can be seen as numbers here. So, yeah, this is our 10th experiment. 6 is over, 10 is over. We'll go to 7th. What is 7th here? Demonstrate word embeddings using word2vec. First, I'll open what is word2vec. So try to understand it. Meanwhile, I'll get some water.
డైరీ బాగా నీకు ఎందుకు నంబర్ గా పెట్టి
Okay. So now our experiments will be about word2vec. This is actually very important concept. I'll first explain visually what is word2vec. I'll get some images to show. So yeah. So word to vec is like last time we saw that, right? Bag of words is one technique. TF-IDF is another technique, like an improved technique. So which from both will usually uh, do it based on the statistics, the matrix calculations and all. But word to vec is different. Word to vec, what we will do is uh, we'll build a neural network for it. Based on the like using the neural network, we will get the representations. It's not a statistical method, it's more of a training. So we'll discuss all of this. So what is word embedding space is this basically. Let's say you have a vocabulary and you want to represent everything, like whatever the words that you have in your vocabulary as vectors. So that will be shown here. You see some related words are here: girl, father, son, mother, boy, daughter. So we can see the relationships here. He, himself, herself. This is one pair. Slow, fast, slowest. These tenses also are available here. Kingu, queenu, manu, womanu, cat, dogs, all of this. So basically, what you have to understand here is all the words which are related to each other, they will be close to each other, right? They'll be very close to each other. And once if they are far away, like if they are not related, for example, man and longest, these two are unrelated, so they are far away from each other. So France and daughter, these are not related, they are far away from each other. But mother, daughter, they are related, so that's why they are closer to each other. So this kind of a space we have to create. We call that as word embedding space. So first let's discuss what is word to vec in theory. Basically, just I wanted to give you the visual representation. So this is nothing but a vector space. In the vector space, we have all the words. All the words will have vectors. Those vectors will be close to each other. Some of them will be close to each other. Some of them will be far away from each other. But the point is, if words are closer to each other, then we call them related words. If they are unrelated, they will be far away from each other. So that's the basic principle from it. So let's understand what is word to vec. Word to vec is a popular algorithm in the field of natural language processing (NLP), used to create word embeddings, which are dense vector representations of words in continuous vector space. Developed by Thomas Miklow. Actually, he works in Google. In 2013, like around 10 years back, it came. Word to vec is 10 years old actually. So word to vec is widely used for various NLP tasks like language modeling, sentiment analysis, machine translation, and document clustering. The core idea behind word to vec is to represent words as vectors in such a way that words with similar meaning are mapped to nearby points in the vector space. This achieved through a shallow neural network model that lends to predict the context of the word based on its neighboring words in the large corpus of text. There are two main architectures for word to vec: continuous bag of words and skipgram. Continuous bag of words. In this architecture, the model predicts. I'll get another image to represent continuous bag of words. So in continuous bag of words, what we will do is first, like this is anyway prediction model. In continuous bag of words, first we will take context and then we'll predict the target word. But in skipgram, we'll take the target word as input and we'll try to predict the context. So here we'll see what is CBOW, what is skipgram actually means. In this architecture, the model predicts the target word based on the context word surrounding it. So in CBOW, you can see this is the target word. Here it is supposed to be. So VT is here. VT minus 1, VT minus 2, VT plus 1, VT plus 2. So given this, you have to predict VT. But in skipgram, you will be given VT. But based on that, you are supposed to predict VT minus 1, VT minus 2, VT plus 1, and VT plus 2. So that's what continuous bag of words and skipgram means. Once a trained, the word-to-vec model produces word embeddings where words with similar meanings or contexts have similar vector representations. These embeddings can capture semantic relationship between the words, making them useful for a wide range of NLP tasks. Additionally, the vector space structure allows operations like vector arithmetic. These relationships such as analogies can be expressed. So here we saw that, right? King, queen, man, woman. So we can actually do plus and minuses here. Like if we remove man from king, that is we subtract man vector from king vector and add woman vector, that resultant vector will be very close to queen vector. So that's what like this arithmetic means. Vector arithmetic means you can actually do plus and minus operations here, which are actually meaningful, right? Because king minus man is like, okay, you keep the royalty, but keep like gender. You are removing gender from royalty, and then you add another gender plus royalty, then it becomes queen. So royalty, like king minus man becomes royalty plus woman, that is royalty plus woman becomes queen. You can do other operation as well. Queen minus woman becomes royalty plus man will result in king, right? You can see like why this happens is because king, queen, woman, man actually forms a parallelogram. So that's why we can see that kind of relation. So this is the basic understanding of word-to-vec. So we'll summarize this now. In word-to-vec, we have first we'll have a vocabulary of words. All the vocabulary of words will be converted into vectors. But how the vectors will look like? The vectors will have the property such that if the words are related, then the corresponding vectors of those words will be very close to each other. If the words are unrelated, then the vectors of those words will be very unrelated. They will be far away from each other. That is one. Other thing is vector arithmetic is possible. Like, okay, you can actually remove slow minus slower plus add fast, then it becomes faster. Slow minus slower plus fast becomes faster. So this kind of a mathematical operations also you can do actually. similar to king and queen. King minus man becomes royalty. Royalty plus woman turns out to be queen. So fast minus faster plus slower is equal to slow. Similar, you can we don't have anything to draw here. Yeah, anyway, it's fine. So you can see my mouse. Fast minus faster plus slower will result in slow. So this kind of a C type, operations you can do. Fast minus faster plus slower will be equal to slow. Why? Because this is the second sentence, like um, past participle. So fast minus faster minus slower, plus slower will become slow. Same here as well. He minus himself plus herself will be equal to she. So that kind of a vector arithmetic also you can do. In this we have two types of algorithms actually. Within word to vec we have CBOW, that is continuous bag of words, and we have skipgram. In continuous bag of words, what we will do is first we'll have the context, that is Vt minus 1, Vt minus 2, Vt plus 1, Vt plus 2, and then that will be given to input, given as input, and our output will be Vt. Similarly, Vt will be given as input, and the context words will be our output in skipgram. So now we will get into the actual algorithm. So try to understand this, like this is actually important. Word to vec concept is important. I'll give you 2 minutes, time. Try to understand this figure actually. This is the important thing. Okay, now we will discuss the code. So from GenSim models, first we will import Word2Vec. Then we'll take corpus. Let me run this first. So first corpus, first we will discuss how to do the training. Then we will try to use the existing, already known model which is trained on huge data, that we will use later. So this is first from GenSim. Actually, we should go to GenSim as well. So this is another library in NLP. So which is very important when it comes to NLP. So NLTK, scikit-learn, and GenSim. These three are very important libraries to learn. I'm copy pasting the document here. So whenever you get some time, no, so go to these links in, like, not just this assignment. In any assignment, if I kept any link, it is useful for you, because you have to learn that first, like what is GenSim and everything. Then we'll come to know how to use it. So we'll have one, quick tour of GenSim now. GenSim is for actually text analysis. So topic modeling for humans. GenSim is a free Python library training large scale semantic NLP models, represent the text as semantic vectors, find similarity, semantically related documents. So this is all GenSim. Why GenSim? It is very fast actually. And also when we are dealing with the streaming data, GenSim can process the large corpora using data streamed algorithms. So like you don't need every data to be fit in the RAM always. So if you are able to stream it, then we will be able to process it. It is platform independent. That means GenSim can run in Linux, it can run in Windows, it can run in Mac OS X, as well as any other platform that supports Python and NumPy. So it is basically for NumPy and Python based wrapper. So proven, like even my company actually uses GenSim. It's thousands of companies using GenSim every day. Yeah, basically a lot of companies, both R&D and product based, use GenSim. It is open source, ready to use models and corpora. So this is how you install it. Pip install upgrade GenSim, or if you are using Anaconda, Conda install -c -c Conda force GenSim. These are all code dependencies. So these are all the functions. Like in the morning we did LDA, right? So here we can have multiple LDAs, latent semantic indexing, non-negative matrix factorization. TF-IDF is also available here. You can see that. Dynamic topic modeling in Python, normalization model, even Word2Vec. Where is Word2Vec? Yeah, Word2Vec. So after Word2Vec, we have Doc2Vec also. So most of the embeddings related documents and everything, like functions are actually available in this GenSim actually. So that is about GenSim. So you understood like what is word to vec first, and within word to vec, what is the vectors, how the vectors look like, and after that you understood within word to vec what are all the type of algorithms. We have two types of algorithms, SIBO and skip-rom, and what is the difference between these two. Now we come to this one. So word to vec model, once we initialize it, sentence will pass the corpus. The corpus is nothing but the set of or list of 2D list, basically 2D list of words. First document is talking about animals actually, dog, cat, pet, animal, and the second document is related to transport, car, vehicle, truck, transport. Third is about fruits and food, apple, banana, fruit and food. So these are the documents we have, and we are passing that as input. Vector size is 2. Here vector size is also 2 actually. If you are able to see it, it is actually 2D. More than 2 is also we can do it, but this should be depending upon the number of documents in your vocabulary, or sorry, in your corpus basically. If you have a lot of documents, then you better choose higher vector size. Usually the maximum that we went to was 300. Otherwise 50 also is fine. Like if you have around some 50,000 documents, then 50 dimensions is also enough. Window size. So how the algorithm works is like this. So this is a window of 3. This window will be passing from over the document. So the quick brown fox jumps over the lazy dog. This is your document, and the window size here is 4 actually. The 4 will be first, because always the word which is in the middle. So this brown is in the middle, right? Left 2 words and right 2 words will be our context. Here there is no left words, so that's why we chose only da as your uh, target word. So you form pairs. Da and quick is one pair. Da and brown is another pair here, because in the window middle word is da. On the right side we have quick and then brown. So this will become one pair. And then next we move a little, like we will move by 1 point. On the left side we have the. So now the target word is quick. So it will form 3 pairs: quick and the, quick and brown, quick and fox. So these 3 will be our new pairs. Now we'll move another step. The quick, brown, fox, jumps. So here brown is the target word. Context words are the, quick, fox and jumps. So here you can see brown will be target word. Brown comma the is one pair, brown comma quick is another pair, brown comma fox is third pair, brown comma jumps is fourth pair. So similarly, we'll move this window one after another. So here window size is 5. So here also window size is 5. The middle word will be target word, and the words which are on the left and right will be your words, next words, like context words. Minimum count is equal to 1. That means the word should at least occur once. Workers are 4. epochs equal to 50, alpha equal to learning rate. Your learning rate equal to 0.01. That is in neural network, right? We will use learning rate. So at each updation, what will be the update fraction that will be decided by the learning rate. So now we have queries like this model. Once we run this, it will learn the vectors for each and everything. Now let me run this. So queries is dog, car, apple. Per query, what will be the vector? So that will be given here. So 2D I told you, right? So vector size is 2. So that's why we have a 2D vector here with 2 numbers. Dog is this, car has these 2, apple has these 2 numbers. So that will be our 2D representation. And now once we get it, we have to find the similarity, quotient similarity between these embeddings. So for for query inquiries, yeah, for these 3, for dog, car, apple, what will be the closest words that we have to find out. So using quotient similarity, if we find out the dog is very close to animal because dog is actually an animal. Words similar to car is transport. So we can see that because both transport and car are similar. Apple and fruit. So apple is a fruit. So both the apple and fruit are very similar to each other. Also, let me try to use pre-trained word to vector. I'm actually downloading let me try this action. uh, now we are actually downloading the complete model. Uh, it takes time, it seems. Out of 100%, only 4% is done. You know what we'll do is we'll discuss 8th and 9th first, then we'll come back to 7. This is not needed. Text. I'll say this is using pre-trained photo and training photo from the scratch. So let this thing downloaded. Otherwise, we can actually wait. Maybe it is about to be completed also. Once this is done, we'll move to the next thing. Okay. This anyway is going to take some time. So what is 8th and 9th? So okay. 8th is about naive bias classification and text block library. And the 9th is apply support vector machines for text classification. Okay, 25% it is done. we have downloaded the model now, pre-trained word to vec model. Correct. So this is a vector of length what? 300. So earlier we created a vector of size 2, right? When we train. Well, let's do the same thing here as well, but a little bit of change. But yeah, earlier vector of size is 2 because we trained it. But now we have a trained model which is of like how much? Almost 2 GB. Almost 2 GB of data, like the model size itself is 2 GB. So you understand like how big the, like whatever we have, we will be in KBs actually. This is in GB. So that much of big data we trained on, and let's see how this will result in queries embedding for this. Let's forget this. Let's see if it works. So okay, we don't need this maybe. You can see now, dog is very close to dogs, puppy, pitbull. Pitbull is also one type of dog. Pooch, cat. Dogs and cats are related. Golden retriever, German shepherd, beagle, pup. You understand like how like good the model is. Like our model is anyway fine. Like only first one is related. Dog is related to animal, true. But dog is not actually related to truck. Dog is related to cat, okay, it's reasonable. Dog related to apple, no. So why? Because we trained for like trained on very small data here. But if you train like this model, what we are discussing here, that is trained on a huge data, which is like if we get the news right in Google. So all the data, like 50 GB, 60 GB of data we trained, and finally we have it like in 2 GB data here. That stores everything. So car is related to vehicle, car is related to cars, SUV, minivan, truck, and then car again, Ford, Focus, Jeep, pickup truck. Coming to Apple, we have apples, pear, fruit, berry, pears, strawberry, potato, grape, blueberry. So if you are able to like download it, like actually try to use it, like whichever word that you want to try, you can try to find the most similar word from it. We'll try another thing here. Instead, we'll try your college name. Let's see if these words exist or not. Okay. For kite, we have GRDP. I think I don't know if this something related to instead of kite engineering, we will try. Yeah, for engineering, we see mechanical engineering, civil engineering, electrical engineering, Billy of head, structural engineering, mechanical maintenance, engineer, all of these are close. For Kakinada, what is close? Visakhapatnam, like not geographically, but meaning wise, Vijayawada, Bhavangar, Rajahmundry, Karaikal, Pradeep, Paradeep, Nellore, Vizag, Kollam. So all the locations are there, like near to Kakinada in the vector space. For Andhra, we have Andhra Pradesh, Karnataka, Tamil Nadu, Maharashtra, Tamil Nadu, Gujarat, Kerala, Madhya Pradesh, Saurashtra, Rajasthan. See, if I search for a state, all the state names are coming. If I search for a place, like within Andhra Pradesh, we are seeing Visakhapatnam, Vijayawada, Bhavangar, all of the like cities related words are coming. If I search engineering, it is giving mechanical engineering, civil engineering, structural engineering, all of this. So why don't you, like, when you get some free time, so just execute this code, you will be able to like try out different things. So it's worth actually. Like it took quite an amount of time to download, but you understand the power of word embeddings here now. So it's like we haven't done anything. We just imported it and then we asked for it. We asked what are the places near Kakinada. We didn't even say this is a place or something. We just said, okay, give me the words which are related to Kakinada or similar to Kakinada. We are getting this. So this is our second experiment, Votovec. So remember this name, Votovec, because it's very important actually. Now we'll go to 8th. Neighbors. Let me copy the. So our assignment or experiment is implement text classification using naive Bayes classifier and a text blob library. First, let's discuss what is naive Bayes, what is text classification, and text blob library as well. Let me. So first we'll discuss what is text classification. So earlier we discussed what is text representation. What is text representation? Text representation is nothing but converting your documents, basically text data, into numbers. Okay, you got the numbers. What do you want to do with? So it can be text classification, it can be text clustering. So now we'll see what is text classification. Text classification is a machine learning task that involves assigning predefined categories or labels to text documents based on their content. The goal of text classification is to automatically analyze and categorize large volumes of text data efficiently and accurately. Text classification is widely used in various applications, including sentiment analysis, spam filtering, topic categorization, language identification, intent detection, document classification. These 6. So, sentiment analysis. Determine the sentiment expressed in a piece of text. So, like we have new movie reviews, right? So someone says that movie is good, somebody says movie is okay. Somebody might say, okay, movie is really bad. So these 3 are like examples of sentiment classification. So if you are talking about positively about something, if I say movie is good, then it is a positive sentiment. If I say movie is really bad, then it is a negative sentiment. Okay, movie is not that bad, but it's not that great. Movie is okay-ish. These kind of words, these are our neutral. Neutral, that means like okay-ish type of review. So why it is like this is one type of text classification. So spam filtering is also another type. Like in your Gmail, you will get promotions, right? And also sometimes you will get spam also from Nigerian friends. You are getting some crores and crores of rupees and all of that. So those are all spam, related emails. You like true emails will be there. Like if you applied for a job, you will get some email, or from your college you will get some email. So those are actually ham. So those are real or good emails. There are other bad emails which are like spams, like messages from some random company or credit cards or some websites like Facebook, advertisements. So all of these mails also you will get, right? So those are called uh, spam uh, spam emails. So categorizing these, identifying, filtering out spam and unwanted emails, that is spam filtering. Topic categorization, assigning topics or themes to news articles, blog posts, and social media. That is also text classification. Let's say you have an article, you want to tag it, whether it's some it can be anything. Like it can be a politics related document, it can be sports related document, it can be health related document. So tagging it based on the content is called categorization, which is also classification only. Language identification. So if I give you some text in English only, but you have to identify if it is in that like you can write Telugu in English, right, in literature. So if I give you some words, you have to understand whether this language, what is the language, whether it's Telugu, Tamil, Hindi, or any other language. Intent detection. Intent detection, actually in my company I work on intent detection. For example, you are building chatbots, right? Like if you open SBI also or any website nowadays, in the left corner, bottom left corner, you will see some chatbot. Okay, you can directly ask some questions to chatbot and the chatbot will reply you. But here the thing is, whatever you are asking, it should be able to identify what is the intent of yours. Let's say you want to transfer some money, it should be able to understand like what is the money in your account, whether you like, it should be able to understand your intent and able to ask the questions. Okay, who do you want to send the money, how much money you want to send it, like on which day you want to send it, you want to send it now or you want to send it later. So that kind of questions it should be able to understand, like ask, right? How it will be able to ask? It will be able to ask only when it understands your intention. Your intention is sending the balance, like or sending money to somebody else. So that is intent detection. Document classification, that is organizing, categorizing the documents in large corpus such as legal documents, research papers, something like that. So this is what we call text classification. So And the text classification, these are all subclass, like sub problems, so you can say sentiment analysis, spam filtering, and all. Similarly, we have in the pipeline of text classification, we have these steps: data pre-processing, feature extraction, model selection, training, evaluation, fine-tuning. So first, data pre-processing. Data pre-processing is nothing but cleaning and pre-processing the text data, which may include tokenization, removing stop words, stemming, lemmatization, handling special characters or numerical values. So in the morning we discussed, right? What are stop words? What is stemming? What is lemmatization? Tokenization. So all of this comes under data pre-processing. And feature extraction, converting the text data into numerical feature vectors that machine learning algorithm can understand. Common techniques include bag of words, TF-IDF, word embeddings, and more advanced representations like BERT embeddings. So this also we discussed as part of a text representation. So we discussed what is bag of words, what is TF-IDF. We discussed what is word to vec. So in the morning we discussed the first part. Like in the very beginning of the second part, like in the afternoon session, we discussed this only. Now we have to choose model selection. Choosing an appropriate machine learning model or algorithm for the classification task. Popular algorithm for text classification include naive Bayes, support vector machines, logistic regression, decision trees. All these are classification related models. In our experiment, we are going to use naive Bayes. So that's the third step, model selection. And finally, we'll train the model. Training the chosen model on a labeled data set where each text document is associated with it corresponding category or label. Then we'll do evaluation. Once you trained it, you have to evaluate it, right? So for evaluation, you do on the text data, evaluating the trained model performance using metrics such as accuracy, precision, recall. All these are evaluation metrics. Fine-tuning and optimization, iteratively refining the model's hyperparameters, future representations, or training techniques to improve its performance. So this we usually don't do it. Only let me remove this actually. This is enough. So these are the 5 steps. It's not just about the text. It's for any machine learning algorithm. These 5 steps are common. First, we'll clean the data. Then we'll represent the data as numbers as second step. And then third step, we'll choose the model. So which model we want to use. And fourth step is we'll train the model. And fifth step is testing or evaluation. So in evaluation, what we'll do? Okay, you train the model. How good is the model? How bad is the model? So that you have to define. So for that, we'll do testing and evaluation. So this is what texting, like this is. So now we'll discuss what is naive Bayes. So naive Bayes is a so naive Bayes, it is a model, probabilistic model or probabilistic classifier based on Bayes theorem with naive assumption of independence between the features. Here is how the predictions. So first, it is actually a model, like a classification model, but based on the probabilities we'll define late. The first step is anyway pre-processing. We don't need to take care of, like it's okay. Like we have discussed this already. We don't need to go into details now. Now the next step is training. During training, the naive Bayes classifier learns the relationship between the features, that is words, and their corresponding labels, topics like sports and politics from the provided training data. It calculates the probability of each word occurring in the documents labeled as sports and politics, the prior probability of each label. So I told you, no, it is about probabilities. Based on the probabilities, the classification will happen. So there we will calculate two probabilities actually. One is probability of a word occurring in a document labeled as sports. For example, probability of Narendra Modi being related to politics. Probability of election being related to politics. At the same time, we'll find like these two will be high values. At the same time, we'll find what is the probability of Narendra Modi related to sports. What is the probability of election related to sports? So for each word, we'll find probability of that word belonging to every class that we have. So that probabilities are first probabilities like this one. And the next probability is prior probabilities. So what is the probability of a topic being a politics, like how many documents are related to politics, how many documents are related to sports. So based on that, we'll calculate this probability. So now classification. So this is training. Under classification, what we'll do is basically this is the Bayes theorem. So like I'll explain you what is this first. So probability of X is your document. Given an X, what is the probability that this document belonging to class CK? So that we will calculate. How do we calculate? Probability of X, probability of CK, given X given CK into probability of CK by probability of X. Here X is nothing but a document, right? So a document contains different words. So here X1, X2, X3, X4 are words. Probability of C1 given X we will replace with X1 intersection X2 intersection X3 intersection X4. That we'll treat that as independent. And now probability of X is nothing but X1 in X1 intersection X2 intersection X3 intersection X4 given this C1 like K equal to 1 here into P of C1. So this part we'll calculate as P of X1 C1, P of X2 C2, P of X3 C3, sorry, X3 C1, P of X4 C1. So this is the final formula. So with this, you will get a probability of given a document, what is the probability that this document belongs to class C1. So this is what the formula for finding the probability. So once you have these probabilities in the training, you will calculate, you will do classification like this. Once trained, the classifier can predict that label a topic of new unseen text data. For each document in the test data, classifier calculates the conditional probability of document belonging to each label based on the words present in the document. It uses Bayes theorem to compute these probabilities taking into account. First, the prior probabilities of each label will be calculated. Then the likelihood of observing the words in the document given each label. So this will calculate. So this is what the second probability is. And the classifier then selects the label with the highest probability as predicted label for the document. So what we will do is this K will change. P of C1 by X, P of C2 given X, P of C3 given X. So all of these we will calculate, and whichever is the maximum, for whichever label the probability is maximum, that label we will assign it to the document. So now we discuss the theory, right? Now I'll discuss the coding part. So first, also text blob is actually not needed here. Like anyway, we'll use it. Text blob dot classifiers import. It's not really that needed, but yeah. Text blob dot classifiers import neighbors classifier. So this is all importing, and then we'll download stop words, punctuations. Now we have the train data like this. What is the training data? We have about 10 sentences, I guess. So the first thing is the football match was intense, which is related to sports. The election results were announced yesterday, which is related to politics. The team won the championship, related to sports. Politics debate was heated, politics. Basketball game was exciting, related to sports. Government passed a new law related to sports, like politics. Similarly, we have all these 10 documents labeled as politics and sports. Two classes we have here. Now we have processing, like first we told we have to process the data first, pre-process it. First we'll convert the text into lowercase, then we will tokenize the data, then we will remove the stop words, and then return finally whatever is there. So this is the train data pre-process. Let me print this actually. So yeah, from the train data. First, the football match was intense. That is converted to football match intense, because the is very common. So like in all the documents we have the. So that's why we'll remove the. Was is also very, very common. So football match intense is here. Next, election results were is removed, announced yesterday is here. So what we will do is we will remove the unnecessary words first. So we have the pre-processed data now, right? This is the pre-processed data. How you will do it? For each text, we are passing that to pre-process function, and that function will clean it and send it back to you. Finally, naive Bayes classifier, you are feeding this training data, clean train data to naive Bayes classifier, and then you train it. Finally, you have test data. So this is your test data, and you want to test, like you want to label this new test data. For text data, text per document, pre-process it first, then text blob pre-process data, classifier, and then blob dot classifier. So this will give you the document and the label. The football team won the game. So this is the text blob. 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 So this is the text blo predicted topic is sports. The election debate was intense. The predicted topic is politics. The basket tournament had some unexpected outcomes. Predicted topic is sports. The government introduced a new policy, politics. The soccer match ended in a tie. Predicted topic is sports. So you can see that okay, all the documents are correctly classified. All the documents which are related to sports got the label as sports, and for the rest of the documents, the label was politics. So this is the naive bias. We'll just recap it once because it's way too long assignment. So first we discussed classification. What is classification? You give a text and you want to label with a class. So that is what text classification. There are different types of text classification, sentiment analysis, spam filtering, and everything. And under text classification, there are multiple uh, steps. There are 5 steps, important steps. One is pre-process it, then convert that to text into numbers, then choose a model, then train the model, and then finally test the model. And then we discuss naive bias. What is naive bias? It is a probabilistic model. Based on the probabilities, we'll try to identify the correct label of the document. So it is based on the Bayes theorem. So this we discussed, and then finally we have the code. Yeah. So we'll now go to the last, because we already discussed the 10th one. The last one is SVM, 9th one. So yeah, apply support vector machines for text classification. So even in 8th also we did the same, right? So in 8, we did the text representation first, then we used naive bias. Now here also we'll do the same thing, but instead of probabilities, we will use the neural network SVM for text classification. And also we will use predefined whatever we have news group data set, which is already available. We will use that. I think we can close it by 345 or 350. So yeah, now we'll discuss what is SVM for text classification. So SVM aims to find the optimal hyperplane that best separates different classes in the feature space. The hyperplane is a decision boundary. So that is like you have negative classes this side on the bottom. You have positive classes on the top side. Now we want to generate or identify one hyperplane which is going through which separates this positive class and negative class, and with a high margin. So that's what we call separating hyperplane with maximum margin. So SVM aims to find the optimal hyperplane that best separates the different classes in the feature space. The hyperplane is a decision boundary that maximizes the margin between the classes. It's defined by the support vectors, which are the closest points to the hyperplane from each class. SVM works by mapping input data points into higher dimensional feature space and then finding the hyperplane in the space. How SVM works? This is how SVM works. First, input data. SVM takes labeled training data as input, where each data point belongs to one of the two classes. Then SVM transforms the input data points into higher dimensional feature space using kernel functions. This allows SVM to find hyperplane that can separate these classes effectively. Finally, SVM identifies the optimal hyperplane that maximizes the margin between these classes. The margin is the distance between the hyperplanes and the closest data points from each class, which are the support vectors. So these are the positive points, these are the negative points, right? So the points which are closest to each other from different classes are called support vector machines, support vectors. And the hyperplane passing through these is called band. The SVM is the hyperplane, which is like this is the margin, the distance between these two hyperplanes, which are going through the support vector machines, or sorry, support vectors is called hyperplane separating. The margin is difference between these two, distance between these two. So the separating hyperplane will be in the middle of these hyperplanes. So that is what optimal hyperplane is. Margin maximization. SVM aims to maximize the margin while minimizing the classification error. It achieves this by solving an optimization problem, where it finds the hyperplane that maximizes the margin while ensuring that all the points that are correctly classified are within the certain margin if the problem is not linearly separable. And then we have kernel trick. SVM uses kernel functions to implicitly map the data points into a higher dimensional feature space without actually computing the transformation explicitly. Common kernel functions include linear, polynomial, radial basis function, RBF kernels. And then regularization we have. Regularization, SVM also incorporates a regularization parameter C to control the trade-off between maximizing the margin and the minimizing the classification error. So a smaller value of C leads to larger margin, but may result in misclassification of some data points, while a larger value of C allows more misclassification, but results in small margin. So these are the main points in SVM. Advantages of SVM is that effective in high dimensional spaces, memory efficient as it only uses subset of the training points, support vectors in the decision function, versatile due to the choice of different kernel functions available, allowing it to handle non-linear decision boundaries as well. And coming to limitations, computational complexity increases with the size of the data set. So as the size of the data set increases, the support vectors also increases, right? So may not be linearly, but it increases. So requires careful selection of hyperparameters such as choice of kernel and regularization parameter. It can be very sensitive to the noisy data. Overall, SVM is powerful algorithm for classification tasks, especially when dealing with complex data sets with high dimensional feature spaces. Its ability to find optimal hyperplanes with large margins makes it widely used in various applications, including text classification, image classification, and bioinformatics. So this is what SVM mean. Now we'll come to actual, text classification problem. So like I told you, like earlier, we will use scikit-learn very much in this text related and machine learning related tasks. So from the text scikit-learn, we are importing news group dataset first, and then we are doing feature extraction. Finally, doing model selection. For SVM, we are doing SVM, like importing SVM we are doing here. Scikit-learn metrics. Finally, we want to evaluate, right? For that evaluation, we are choosing accuracy score. So these are all importing. Once importing is done, categories. In this test news group data set, we are choosing like 1, 2, 3, 4 categories. Atheism, Christianity, graphics, and medicine. So these 4 we are choosing as our topics, and then we are choosing the subset of the data, 20 news group data. Finally, we do the TF-ID of vectorization. First, we are initializing it. Once we initialize it, we will fit the data into transformer. Finally, we given the text data, we split into 70-30 size. So with random state 42. Now we will get X train, X text, Y train, Y text. So we are choosing linear kernel. For this example, linear kernel is enough. And then we are fitting the data, SVM classifier, predictions. Predicted SVM classifier is like predict. We are passing the X text data, and then in result we will get the predicted labels. For accuracy calculation, we have a model, or we have a function accuracy underscore score. First, we'll pass what are the true labels and what are the predicted labels. So if we pass this, this accuracy score will calculate the accuracy, and we are printing the accuracy here. So in this case, we are getting about 96%, because most of the data like we considered was very diverse data, which are very well separated actually. One is about atheism, another is Christianity, little bit related, but fine. Graphics and medicine related. So we discussed in this session SVM, like how it works, what is the theory behind it, and how to use TF-ID to convert the documents into numbers or vectors. And once we have the vectors, that vectors can be passed to SVM classifier. The classifier will predict or understand the labels, and given a test data, you will try to predict the new data. So yeah, this is about text classification using support vector machines. And we ended this with the 9. So today we covered all 10. We'll see, like either today or not today, maybe. Maybe on Monday we'll take 1 hour class to repair, like to complete this entire thing, 11th and 12th. So it is actually about sentiment of identifying the identifying the identifying the sentiment, and then detecting the hate speech. So this will cover maybe on Monday. I will talk to Ramakrishna sir, your HOD, and decide one slot for it. It will just take 1 hour maximum. We'll cover this later. I think yeah, your buses also are coming here. I think for today the section is over. Anybody available? Okay, for today the session is over. So anybody like who is there, maybe you can. So is there an admin here? I think for today the session is over. Any class CR or someone? Is there anybody? Okay, anyway, I will close the meeting by 3:55. Like, yeah, in 4 minutes I will close the session.